It's my pleasure today to welcome Professor Veera Sundararaghavan, who's a professor of aerospace engineering here at the University of Michigan. And Veera's research interests are in the field of computational material science, computational mechanics, and materials informatics. He's authored over 100 journal papers and has worked on a lot of programs and is a recipient of several awards, amongst which are the NSF Career Award, the DTRA Young Investigator Award, and the Defense Innovation Award. He also is an AIAA Associate Fellow and an ASME Fellow. So thank you again for accepting our invitation, and I'm really looking forward to it.
Pleasure. I work in different areas, mostly related materials, and microstructure evolution. So maybe talking in the context of microstructure evolution, how much of this you do in the center. You want to make this talk more general, talk about tools you can use for different problems. It doesn't need to be restricted to materials. That's my area of expertise. Modeling and it's fitting fracture. So I want to give you start with some questions. Let's start with some questions here. So if I want to first define something and then ask the question, what are the dimensions? So there is a definition. It's a concept of intrinsic dimension. So intrinsic dimension for a data set can be thought of as the minimum number of variables needed in the representation of data. Those variables are called state variables. Example I gave here, for example, laws of thermodynamics have state variables such as temperature, pressure, energy, and entropy. So those are some state variables in the laws of thermodynamics. But in general, it's not related to any data that you have. Take from GPT, for example. That GPT works in a latent space of 128 dimensions. That's what's the intrinsic dimension. Every prediction it does is based on that dimensional space where it stores all. That's a huge dimensional space. Most structures, materials, any physical system will eventually end up having very few state variables. For example, thermodynamics, you have very few state variables. Explain just about everything, all the laws. So I want to ask you this question: what is the intrinsic dimensionality of this data? So what you are given, for example, is some X, Y, and Z. So I give you a table of data with this X, Y position and Z position. So the question is, what is the intrinsic dimension? How many variables define this data set? Just by looking at this data, you might think there are 3 variables, X, Y, and Z, that define this data set. You can plot this. So when I plotted this data, I get this kind of a helix. The question is, what is the intrinsic dimension? So just by looking at the data, it's not easy to say it's what is the basic dimension that defines this. So there has to be some tools developed to get the answer. So I'm going to talk about what kind of tools you need to get the answer to this question. But give you one more hint, or if someone wants to try it, it's the dimensionality of the space. What's the minimum number of variables? 2. Guess it. 2 is a good guess. It has to be less.
One. It's a curve, right?
1 is the right answer. It's not very easy to say just from the data. So I'll show you one more hint.
Isn't it 1?
One is right. One is correct, but I want to show you why.
Okay.
So the answer is based on the equation. So this data set eventually comes from this equation. It says x equal to something, y equal to something. But all these variables only have one variable here. If it is t, you get all these points. Just by changing the value of t. Going from 0 to 1, you can generate all these points. The dimensionality is 1. This one variable t generates this trajectory. So it's just a one variable data set. This is a simple example just to give you motivation of what is intrinsic dimensionality. Intrinsic dimensionality is that just tells you what's the minimum number of variables you need to define a data set. You might never know this equation. From the data, it's not easy to even figure out this equation. That's a very hard problem just to understand what equation is plotting. All you have is some data points, but with the data, you can have some tools that can tell you what is this new, what is the answer to this intrinsic dimension. Give you some more definition of intrinsic dimension. Intrinsic dimension of this data set is one. Right? By definition, single variable defines this data set. We call these variables as state variables. So those are the temperature, pressure, or something. State variable is not unique. Why is it not unique? Is I can use 2 times t as a state variable. It's still a state variable. I can use 5 times t, 6 times t. Any multiple of t will work in this case. That forms a state variable. So that's not unique. There's no unique answer, but there is a unique answer in the number. Just need one state variable. But given the state variables, the data can be generated. So that's the generative networks. All these advanced neural networks, they're all generated networks. They work in that small dimensional space to generate all the data. I want to show you one more question. Sequence of microstructure images from a single simulation. So you run a phase field simulation. Can be any. Let's say you do a CFD simulation. Start from initial conditions. And let's say flow over a cylinder. You capture the vortices. You have the one forming vortexes, forms at the drop. You have a complete video. What's the dimension? Who wants to guess? I have the answer here. You need to tell me why. So the reason I said the dimensionality is 1. Again, the reason I said the state variable is time. So why is time the state variable? Because it's a video. So in a video, every frame happens at a certain time. That's the only state variable. So all that helix trajectory, you can think of it as a time variable, generates all this data set. So if you don't believe me, later I'll show you simulations where I take the entire phase field simulation, I can plot it on a single line. But you can arrange that as a single line, although it's a very complex data set. Another answer where it's answers. One is serial section data. So you take a microscope, take serial sections of your have a block like this. So brains. I take a serial section. I have tons of these images. That's my database. Again, the dimensionality is 1 because all of this are defined by just the C variable. Position height defines every section. So even though the microstructure is high dimensional, there's only one variable defines all this. So how do you find the number of variables? Is what I want to talk about. But for that, another question is you take the pendulum oscillating. I have a video pendulum moving. The second question I would have is what are these state variables? Can you identify? You know, for a pendulum that's swinging, I can take all these images, take a video. I can say the state variable is calculate the state variable based on the images. But can you tell me what is the physical principle behind the state? In this case, there are 2 state variables. One is the position, other is the velocity. For one video, there's only one state variable. We know time is a state variable for video. But when you stop the video, that's a state variable. But actually, there are 2 state variables because you can make 3-4 videos starting with different initial conditions. So that initial condition itself is the state variable. It's not the time where you stop the video. Those initial conditions are defined by position and velocity of the mass. So if you have a pendulum, you know the position velocity of the pendulum, the mass of the pendulum initially at t equal to 0, you can predict the entire trajectory. So those are the state variables. So in general, the state variables tend to be the initial conditions of your differential equation. Those are the state variables. We can generate any trajectory from that differential. So we'll answer some of this in the talk to identify what are these state variables, what is the physics behind these state variables. Can you predict future trajectories once you know how these state variables this time? To answer the question, first we need to think about a low-dimensional manifold. The helix I showed you before, it's already a manifold of one-dimensional manifold. Another common one is called a Swiss roll. This is called a Swiss roll. You can get these cakes from Kroger. They're called Swiss rolls. They're like this. They are in effect 2-dimensional. Like just like the helix was 1-dimensional, Swiss roll is a 2-dimensional surface. All you have is the points. You'll have x, y, z coordinates of these points, and then you'll have to estimate it's 2D or 1D or 3D. Those coordinates. Another example is image data. So these are binary data sets. So if you have 3 pixels, 3-dimensional, in this case, every pixel takes a 0 or 1. And then you can generate this whole data set, but it's a sparse data set. Your data is only on that vertex of a cube. Every vertex of a cube is an image. Anything in between is a non-binary. So that's called a sparse data. This one I call continuous data set. Points can take any variable. This is a sparse data set where the points can only lie on certain points. You have no points in between because a binary image cannot take a value of 1/2. Binary image will take a value of either 0 or 1. So those are called discrete data sets. So I will talk about what are the metrics to use to find the dimensionality of a continuous data set versus a discrete data set.
Can I ask you a question? In this picture, when you show the manifolds and you say contains all images with phase fraction 2/3. Is that, but that plane seems to also have some images with 1/3. Am I reading it correctly?
That's right. So this one plane and rod.
Yeah.
Only that plane will have two whites. Two whites.
Oh, two whites.
So 2/3 phase fraction. Oh, black is not the phase. One is the phase fraction. So two ones. So this plane will contain all the phase fraction.
See, no other plane will have that.
Any other plane will have others.
I see. Thank you.
Because phase fraction is a linear expression. X1 plus X2 plus X3 is varying. X1 plus X2 is 1. So that's a linear equation. So immediately.
Thank you.
Intrinsic dimension, we have to make some assumptions to get that answer I was talking about just from the data set. So you only have XYZ position. So you would assume samples are identically distributed, independent. It's all statistics. Here is some statistical approach. The mapping between latent space, when I say latent space, these are the state variables. Ambient space are the images. So you have a bunch of images of a microstructure and one variable that define as the distance between 2 points in the latent space, the ambient space is same as that in the latent space. So this is called isometric assumption, which you can see from the Swiss roll that globally this distance is maintained when your Swiss roll is curving. Take a flat sheet of paper and then you just roll it. This distance doesn't change. You roll that sheet, it's just a rotation. So that's the assumption. And then the data points will be uniformly distributed. This is the most important assumption because eventually you will see that the intrinsic dimension is the dimension in which the data is uniformly distributed. That's why the helix has a dimension of 1. Because on the helix, the distribution is uniform on that one dimension. That's the point. So the curvature doesn't really talk about dimension. It's just that the space space can be curved anywhere. But overall, that data should be uniformly distributed on the curved space. That's what we're looking at. So in a sense, the notion of distance between images has to be clear. It has to be a geodesic distance. It's not just the gradient distance. It's the geodesic. Usually, this geodesic distance is very hard to find. So we instead use local neighborhoods and look at Minkowski metrics. Minkowski metrics are basically L2 norm is one of the Minkowski. It's a 2 metric. L1 norm is a 1 metric. It tells you the distance between any 2 points. So the usual distance we know, which is square root of delta x square plus delta y, that's called a 2 norm. So this is root mean square. You take t equal to 2, you take a square root. It's a square, and then you take the square between the coordinate. Take the square root, that's the L2 norm. That's the one we usually use for distance. But there can be other distances, like Manhattan distance. L1 norm, the distance where if you want to go from A to B in New York City, you have to go through those blocks, and you only follow perpendicular lines. So that's a larger distance. You don't go on the diagonal. That's called a Manhattan distance. It's called L1 norm. So those are. So your answer depends on the metric that you use. That's one of the things we found out this paper. There are lots of proofs. I'm not going to give you the proof, but I want to give you the concept. The concept is if you take your data set, you plot on the x-axis the distance between every neighbor. So k is the neighbor. So I take this 1 point. I find the distance between this point and the nearest neighbor. I call it T1. I find the distance between this point and the next neighbor. I call it T2, third neighbor, fourth neighbor, fifth neighbor, and so on. So every kth neighbor, I plot the distance, log of the distance. So I plot the k numbers. So k is 1, 2, 3, 4, 5, etc. So first neighbor, second neighbor. It will always fall on a straight line. You can see any data set. It's sufficiently random enough. You have enough data points, they'll all fall on a straight line. There's a reason for this. It's because of this. So it says the average number of points that fall into a hypersphere around point 1 will be proportional to the volume of the hypersphere. The number of points that fall inside a sphere will be proportional to the volume of a sphere. Hypersphere can be anything. Circle is a hypersphere in 2 dimensions. 4-dimensional sphere is a sphere. In general, the number of points that fall inside a circle will be proportional to the number of points that fall. The area will be proportional to the number of points. So if you take a log on both sides, you will get mu coming out. The slope directly is the intrinsic dimension. All you have to do is do this plot of distance to the nearest neighbors versus the number of points. Slope directly goes to it. Right on the helix data, you directly get intrinsic dimension to be 1. But this is done locally for every point. So every point gets a curve like this. So this point will say I'm on a one-dimensional surface. This point might say I'm on a 2-dimensional surface. This could say I'm a 3-dimensional surface. Every point will have a different slope because this slope really depends on how many points are around it. Very sparse data set, so you don't have any points. The way it's actually done is you do it for every point and then you poll it. You do a histogram and see which number is most common among all the points. If 90% of the points are saying I'm on a 2-dimensional surface, the answer is 2. 50% of the points say I'm in a 2D surface. 50% give you a 3-dimensional surface. The answer I would say is 2.5. Those numbers are usually taken as a mean of the histogram, so you'll get decimal points in all these cases. But you'll get an estimate whether it's 2D or 3D. You usually take the upper values. There is more statistical understanding of this through Poisson distribution. So Poisson distribution tells you how many the probability distribution of finding k minus 1 points within a distance of r. It's usually given by a Poisson distribution. Poisson distribution used in many places. You can use it for finding how many people are standing in a queue at a certain time, but how many people are waiting for an Uber car at a certain time. It's not Poisson distribution. These points can be number of people, distance can be time, anything can be just a parameterized. So from the Poisson distribution, you can get an estimate of expectation for distance. Again, the exponent comes out as intrinsic dimension. So that's one of the things I'm going to show you. All of this are related to the statistics of the process. The dimensionality directly comes out. These are called Minkowski circles. They tell you what is the distance. How do you measure a circle? Is in the usual sense, a circle is this blue line. It is an L2 circle, which means from the center to every point you have the same distance. It's called an L2 circle. This kind of structure is also a circle. You'll laugh if I say this is a circle, but this is a circle when you use the L1 norm. The L1 norm gives you this circle. The red one is the L infinity norm. This is a L4 norm circle. So the circles means the distance, the L4 norm of every point from the center of the plane. So what's the right estimate of the distance to be used for these cases is what I want to find. Whether it's an L1 norm or I'll skip this one. This is a Swiss roll data set. But in general, what we see is if you use any norm for a continuous data set, the answer is the same. Whatever norm I use, there's a 2 norm, 3 norm, 4 norm, 5 norm, 6 norm, so on. The intrinsic dimensionality remains the same for a continuous data set. It's very interesting that it doesn't change with the norm. And we proved it because of the Poisson distribution. I think the ratio going back to the Poisson distribution. This equation itself signifies mean distance ratio will be independent of parameter only for a continuous case. So we take a ratio of any two distances, this one will cancel off. So, and this has no parameter p in it. So the L2 norm or the L1 norm give you the same answer. Later we saw some papers where there was some confusion. So I'm going to go to papers. Main point I want to make is there have been papers coming out like this. For example, This was a physics-based machine learning paper. What they were trying to do was understand videos. They took a video of a pendulum, a video of a fire. They took some reaction diffusion problems where they put a chemical inside a liquid to video. They found an answer to be 2 in this case. Intrinsic, this is an intrinsic dimension. That video was 2. The ground truth was 2. In some cases, they found double of it. So instead of 2, they found a 4. Instead of 4, they find close to 8. 2 find a 4. So I was wondering why in some papers they're giving double answers. It's really related to the Minkowski norm. They were using L2 norm in this paper. L2 norm is not correct for discrete data sets. I want to show you that whenever the data becomes binary, like I showed for those 2/3 volume fraction images, you cannot use L2 norm because it will give you double answer. So this is recently we wrote a paper. Skip some of this. There's a principle behind this. Is that if you use a binary image, take this image. This is my image starting point, and I have a variety of these images with different locations. Should give me an intrinsic dimensionality that is 2, because the location of circle is only dependent on x and y coordinates. So there are only 2. It's a 2-dimensional data set. I'll show more of this later. If you use a binary image, you draw that scaling for intrinsic dimension. You get the dimensionality increasing with the Minkowski distance. The choice of your Minkowski, whether it's L2 norm or Manhattan distance, give you different answers for the intrinsic dimension. That's what we saw in this. Later in this paper, we proved 4 theorems. You can see this. All the proofs can be found in this paper. A couple of years back, we worked with Air Force on this. They were interested in 3D printing. They want to understand what are the basic variables and design microstructures. So we did more theoretical work to understand this ideal algorithm. So series of 4 theorems. First theorem says if it's a analog data, which means it's not discretized, it's not quantized, then for a helix or a Swiss roll, you will get the exact answer, no matter what instrument you use. But theorems 2, 3, and 4 tell you it depends on quantization. As soon as you quantize the image, say it's an 8-bit image or a 16-bit image, you will have to use the L1 norm. Any other norm will increase. So I said for any other norm, the dimensionality will be higher than quantization. That's what I spoke. Example is here that you have a phase field image. Grain sizes grow in a phase field simulation. We find that use an L2 norm, you get a double the dimension. So 1 to use an L4 norm. L4 norm will give you 4 this answer. So it basically multiplies the dimensions. So which was interesting because just the choice of the distance will change your intrinsic dimension. We didn't figure this out. Earlier, there are lots of papers still coming out saying intrinsic dimension, double of it, just a norm. You have to use L1 norm.
Can I ask you a question? When you define the Minkowski, it's the distance from a point, and you compute that for a number of. So is that so? There's a discretization involved in the distribution of points, and then there is what you said is quantizing. If the data itself is quantized or not.
Right.
Is that correct?
Right. So
these points are independent of how you distribute your points.
it's independent of how you distribute. So points can be anything, then it's analog data. So if it's like let's say you do some measurements of temperature.
Yes.
So that can be continuous. You can have 36.58 as temperature, 59. So that's a continuous distribution. There you can use any norm to give you the right answer. As soon as you quantize, saying my answer, my temperature can be 36, 37, 38, discrete numbers, you rounding it off, then you have to use the L1 norm. Any other norm will give you double, increased dimension. That's what we proved. And when you use those volume expansion, so I expand the volume, see how many points fall. You have to sell. L1 norm gives you the lowest. It didn't prove that L1 norm is the exact answer, but it gives you the lowest basic dimension. So it's more of quantization of the image itself. It's binary or a continuous image. Why are these theorems important is what I showed that you see a lot of papers where you larger answers because they're using the wrong norm. Once you see a binary data, you should use L1 norm. If you use a base case data, which is continuous, you can use any norm you want to get the data. For people who are still getting a hang of what is this intrinsic dimension. I have a bunch of examples here just to show you how to find it. Like I said, you plot a histogram, so every image is a point. These images are 128 square, so the image is a point in a 128 square dimensional space. If you plot a extremely large dimensional space, this whole image is just one point. It's just a vector of x, y, z locations in that dimensional space. For every point, you find what is the dimensionality based on its neighbors, and then you plot a histogram of what each point says. 50% of points say I'm in two-dimensional space, I'm in 15 space. One dimension will come out as a histogram. So in this case, what I've done is, for example, randomly placed rectangles. Take rectangles, you randomly place them, generate a data set, you test the dimensionality. Answer is 4. The dimensionality of all these images is 4. Even if you have a million images, you just move the points around, it's still 4 dimensional. Because all you're doing is you're varying the size of the rectangle, then you're changing the location of the center. So you're changing length, height, x and y location. So there are only four variables that define this entire data set. Just like the helix had only t that defined the whole helix. Only 4 variables changing every single image. So it's a 4-dimensional space. Same thing here. So here I keep the same rectangle size. Then I move the rectangles around. It's a 2-dimensional. Answer is 2. If I rotate it, that rotation becomes a variable. So the answer is 3. The other example is square. So take square. Take the same example, but now you make it into a square. The answer will now be 3 because length is same as the height, reduces one variable. So what that means is you have an enormous data set, but really, even though each image is 128 square dimensional, it's only 3-dimensional. You can plot this whole data set in 3 dimensions. It's very fascinating. It really makes a difference in how you think of calibration of your data for the experiment. So all of this, it's really, if you can find the dimensionality, it's a simpler model. You don't have to use variables in your calibration. So you have 3-dimensional space. So how to find the state variables? So you can use neural networks to do this. Simplest is autoencoder. So you take an autoencoder, the neural network, what it does is takes input data, and then you make a neural network that is having lower number of neurons as you go forward, and you can stop at the intrinsic dimension, stop at 2 dimensions for a Swiss roll. So you can give the Swiss roll points. It'll be I'll show you later how I expand the Swiss roll to an image. But then you can bring it to 2 dimension, and then you can plot this. This is called a latent space of a neural network. This is the latent space, and you can plot it, and you can see the trajectory. You can understand principles of how the data is distributed from the latent space. You can also go ahead and use a decoder. The decoder will reconstruct this. The error function for a neural network will be what's coming out minus what's going in. What this network really trying to do is compress the data. It's trying to bring the data back to intrinsic. One interesting thing we found, we haven't written papers on it, but if you cannot bring your data below the intrinsic dimension, that's one way of actually finding the intrinsic dimension. If you use a neural network like this, take a Swiss roll and bring it to 1 dimension, you can never do it. You start looking at your errors from the neural network, be extremely high once you go below that bottleneck. Intrinsic dimension is a bottleneck for your data set. How do you autoencode a latent space? Here's a simple example. It's a toy example. I take a Swiss roll. I take every point of the Swiss roll. Then it has x, y, and z dimensions. It has 3-dimensional. It's a 3-dimensional space. And then I take those 3 dimensions to be the location of the center, x and y, the size of the circle. So every point has x, y location. It becomes the center of the circle, and then the radius is defined by the z-axis. So that will generate a huge database of circles in a background. It's a matrix precipitate, I call it. And then I run it through this encoder, autoencoder, and bring it to 3 dimensions. You can bring it actually to 2 dimensions because Swiss roll is 2-dimensional. Open it up, be a rectangle. But how does the space look like? So I try to plot this. It looks like this. So neural networks already figured out the image data set is lying on a Swiss roll. Just by bringing it down to 3 dimensions, you plot the 3 numbers that come from the 3 neurons that sit here. They look like a Swiss roll. So it's already figuring out the nature of the data, which is very interesting. And that's how really neural networks work. It's the structure of the data. That's how GPT works so well, is because it's modeling the latent space. all the words. So you have another example, a few more examples we have done. This is a generator space. This is Swiss roll I just showed you, but this is another example. This another I want change it to images. I bring it to the latent space. This is one less than the one greater than the latent space. This is the latent space. The latent space itself is a straight line. So for this data set, like a helix, the latent space is just a straight line. This is your intrinsic dimension. It's a one-dimensional object. This one is a two-dimensional object in this. So neural network actually did not open the data, it actually crushed it. So we crushed it from the top. So we take this and then we crush it from the top like this. So it gives you a two-dimensional space. So what do we do with this is we try to understand dynamics in this latent space. So here's an example of a single microstructure simulation. Previously, I told you that dimensionality is one, a phase field for an equation. Let's say you take a differential equation, start with the initial condition, you propagate. Your dimensionality is just the initial condition. So everything else is coming from that equation, differential equation. So in this case, you have a whole bunch of complex phase field simulation. You have a bunch of equations for the energies and all that. At the end of the day, you run it through ID simulator, send it to a just see a line. Basically, a one-dimensional space. The dimensionality estimate is 1. That 1 is the time. Every point corresponds to a time snapshot of the image. You take this point, take it through a decoder, and you get back this image. So you have basically compressed the whole database into one-dimensional set. All you need to do is store the neural network, store that one dimension, you have compressed your data. Here's an example of multiple phase field runs. All these runs are one-dimensional, but then they fall in 3 dimensions because I have 3 simulations, each one following a different trajectory. This is a decoder output. So decoder basically tries to reconstruct. There is some loss in the reconstruction. It's not trained very well, but if you have a big enough network, you can actually get on. The losses will be 0 because you're at the intrinsic dimension. If you go below the intrinsic dimension, the losses will be very high. You will not be able to reconstruct. I want to talk about one specific application. Go ahead.
You got 2 slides before when you said that for the single grain thing, the intrinsic dimension is just the time dimension. So that means does that mean it's storing just one value of time as a state variable?
Yeah, it's just organizing your images as a time sequence. So all of these were this is the actual data set. So this is the initial condition. Then you run some equation that moves these grains out. So it goes like this, and then you have new grains forming this equation going on. It's following some very complex differential equation. At the end of the day, every image, the tag for each image is the time. So you would end up having this image going to this point, this image will go to the next point. So it'll be a sequence of dots. Every dot can be decoded by the.
Why does it look like that?
Because I didn't do a one-dimensional. This is not one-dimensional. I plotted it in 3 dimensions. So the previous one, I actually brought this back to one dimension. So this is the same idea here. I took this, I brought it to 3 dimensions, and then I bring it back to 1 dimension. Straight. So the phase field will also look just like a straight line. It will in fact be organized by the time. It will be single shape.
Can I ask one? I had a very similar question. When you said time, is it saying that it's not able to compress each image into a lower dimensionality that effectively could interpolate, in sense, between frames, if you ask? Is that the conclusion?
That is the conclusion. Every image is a dot. Every image is 1 point
Or the
one number.
so interpolate? Can I ask you? Suppose I was imagining each image was like say a voting, an image that decayed in time.
Right.
So now everything really is related.
Yep.
Everything is a circle, whatever,
Yep.
but just its amplitude changes.
Right.
Will that
It's
will
still
the
one
dimensionality still be one?
Still one dimension.
Still be.
As long as you have one equation with the one initial condition, that initial condition is because every other image is coming from that one equation. The only variable in that equation is the initial condition.
Oh, I see. So that is the meaning. Thank you. That's it.
It's hard. The helix gives you some idea, like they show the helix. There's only one T in that whole equation. Even if you have a very complex differential equation, the initial condition is all that is
That's
changed.
the dimensional
Everything is
initial
deterministic.
value.
Everything is deterministic. That's it.
Thank you.
In the vortex example, what if you change the viscosity? You get a different.
Viscosity will be another dimension. Whatever you change is your next dimension across the data set. So if in this, so if your initial condition is one intrinsic dimension, let's say your initial condition is how you set your fluid densities initially. Density will be the initial one. For all your simulations, you run 50 simulations with different densities. They will all lie in a straight line. Density is one of the dimensions. Second dimension will be time because you have a video. The time differentiates each microstructure for that given density. If you change viscosity, that will be a third dimension. All of this will be just three dimensions. So your entire data is 3D. Those are the only things you change when you generate the data. Whatever you change, whatever numbers you put in when you generate all the data sets, that's your intrinsic. So everything else is deterministic. That's the key idea of intrinsic dimension. So that's what you need to answer. So these are good questions so we can understand what's going on in intrinsic dimension. It's all in the equations. So here I run 3 phase field simulations. So I already get an intersection. So locally, even the dimensionality can change locally. So in this case, if I hold this point, it will say it's 2 dimensional. If I hold this point, it will say 1 dimensional. So locally, there are some changes. That's possible. Globally, it's still 1 dimensional. Here, so I've put some applications. So these are some examples you can think of already if you want to try a new project. You can take videos of your simulation, identify the driving process variable. And you take, if someone doesn't tell you, I ran this simulation with a differential equation, change the viscosity, for example. They just give you the data, you run through this intrinsic dimensionality. You can estimate what they changed. So that is a, so example is you take a video of an aircraft, and you can maybe use Schlieren and you can measure these vortices. You can understand what are the process variables, how does the wing shape affect this? So you're changing your wing flap, change your angle. The angle will be an intrinsic dimension. Can you actually identify what is the effect of that intrinsic dimension on the vortices? So you can use those videos, use the videos to identify the number of dimensions. Cannot do time. That makes sense. And you can also generate, you do an experiment, take few slices in an image. You can also interpolate between slices. Find out what's the next slice, most possible slice by doing those neural network information. So you can also use for interpolation, extrapolation. How am I doing on time? Yes. Okay. 15 minutes. I have something I want to show you. It's very interesting. Recently, we've been doing this to understand differential equations. So let's say this point, you have a differential equation that takes it to some target. And you develop a neural network that follows the physics of this trajectory. Right now, what the autoencoder does is it takes the data, crashes it to the intrinsic dimension. It does not follow physics. You can see that because it's not identifying the Swiss rule. So going back to this is the physics. It's following, the points are following some trajectory like this. Didn't get the full physics because there are some intersections. It got the directionality. Some of the structure itself doesn't look exactly like the Swiss rule. Can you make it obey this? When you run the autoencoder, special autoencoder, you get back my Swiss rule. Now giving you something that looks like a Swiss rule. So you want to put some physics inside this autoencoder. That's what we focused on. So going back to this, I want to show you some example of a pendulum because this is very simple. You have a pendulum oscillating, you get a differential equation. The CFD has a constant differential equation. Here we have a simple ODE, but it defines every time snapshot of the scene. Like I said, the intrinsic dimension is the initial condition. The initial condition is velocity and the angle. Initial velocity and the initial angle. When you sit in a swing, you have the initial angle that you start with, and someone pushes you, gives you initial velocity, and then you plot swing. But if you plot velocity versus angle for one trajectory, it turns out to be a circle. This is called a phase space in dynamics. Phase space is 2-dimensional. And then you have, there is a point in the phase space where it's no longer oscillating, it's actually going like this. So what is this? This is when you push the pendulum so hard. I wouldn't suggest you do it. Your kid sitting on a swing. If you push it extremely hard, it'll go all the way up and come. push it very so hard that this pendulum goes all the way up, comes back, and that's what this is. So at a point, it will transition going from an oscillating motion to a complete circle. That's what you see here, and there is this bifurcation that happens when you convert from oscillation to a complete circle. So this is an example of a simple pendulum. In effect, this never happens because there is air resistance. When you take a video of a pendulum, it will always come to a stop because there is always air resistance going on. So your trajectory will end up being a Swiss roll, be a spiral going to zero. Eventually, the velocity and the angle will all go to zero. Pendulum will stop right like this. Zero velocity, zero. So that's what happens in reality. So we want to understand how do you model this. So we started looking at Lagrange's approach because in Lagrange approach, the intrinsic dimension, if you think of it as just a Lagrangian, if you define a Lagrangian, you can get the entire dynamics. So instead, we looked at a neural network that took in the two initial conditions, brought it back to the Lagrangian. And then we set up a loss function in the neural network. That's basically the Euler-Lagrange equation. This itself is a loss function, the difference. Take the L2 number of the difference, gives you the loss function. The pendulum's equation is this is a Lagrangian for a pendulum. Then if you put it in the Euler-Lagrange, you see the differential equation that defines the pendulum motion. In a general case, when your input is a vector, means input is an image. Think of an image of x, an image of x dot. Take a video of your vortex. The video gives you initial condition. The first frame of your video is your x. X dot is the difference between the first and the second frames. You can also get acceleration, which is coming from the video. You can get 3 frames of the video and get acceleration from the video. So you can get all the information about displacement, velocity, acceleration. Just taking a video of experimental video of a physical phenomenon. Then you can run through this Lagrangian network, construct the correct trajectory in the phase space. So in this example, I'm showing you how the neural network works. So instead of giving you random trajectories, now it's actually following the phase space trajectory. So this is a neural network output. Here I did a Hamiltonian neural network, slightly different, but philosophy is the same. This autoencoder is a loss function that has an idea of what the structure of this problem is based on the Hamiltonian, based on the Lagrangian. So it can get you the right trajectories in the intrinsic dimensional space. So this is trained data testing back. I want to show you the energy itself. What does the neural network give out? So I plotted the output of the neural network. Output is the Hamiltonian in this case. It's a Hamiltonian network. It gives you the energies, the energy. Hamiltonian is the energy, so it gives you the energy of the as a function of velocity. Higher the velocities, the state variable 2 is the velocity. Higher the velocity, you have the supply. And plot some error from analytics. So it's able to get this trajectories correct. Next, you want to do a damped system because in reality, everything is damped. You have pendulum will never oscillate forever, it will always damp. So there is air resistance. So the example is something like this. You have a spring, you have a damper. You oscillate this mass. The phase space, the initial condition for this differential equation, right? This whole thing is just one differential equation. The initial condition is position velocity. So that's your intrinsic dimension. For the phase space, your position velocity. Start from this point, and then you start this spring, and then it will start to deviate from circular motion back to zero. So this is a case of a dissipative system. They always look like a Swiss roll. There are some principles of this phase space. Intrinsic dimension, physicists call it phase space. I call it intrinsic dimension. It's more judgment for all data. But if you go to physics problems, typically called as a special name for the space space sometimes. All the initial conditions. Basically the initial conditions. For that differential equation. The phase space for a conserved system is curve-free. Phase space with dissipative systems and net curl. So those are the two concepts you need to understand. In one case, not from this point, you reach back that point. Line integral, quantum integral goes to zero. Here it's this is a vortex, so it is irrotational. We call it irrotational in fluid dynamics. So this has a vorticity. The term used is vorticity. Phase space has a vorticity by itself. So how do you generate these trajectories. So we looked at what is Lagrangian doesn't work in these cases. When Newton developed his equations, they're all based on conserved systems. These are not conserved, so you cannot use Hamiltonian Lagrangian mechanics because of a conserved system. So we tried to go further, a little bit more math here, but the concept is if you have a diffusion equation like this, you would have to use what is called a dual Lagrangian. Dual Lagrangian splits your answers into two parts. One is a real part, which is what you see, and another is a dissipative part. So overall, globally, the system has conserved quantities, but it's a combination of two phase spaces. In one phase space, you get all the energy. Other one is a sink. One is accumulating energy, other is dissipating energy at the same time. So you get two equations. One is called diffusion equation. One is called undiffusion. I made up this name, undiffusion equation. Undiffusion simulates what is lost. So if you have heat being lost from a system, that heat goes to a sink, which is also tracked at the same time. I'm going to skip some of this here. I want to show you example of this is an example of some trajectories. We start with different, these are diffusion equations. They start with different precipitate structures, run forward problem, inverse problem. All of them will dissipate to zero because these are dissipative equations. Eventually, this yellow will dissipate everywhere. Think of dropping a red liquid into water. Eventually, it will become pink. Water will be just dissipating everywhere. So this droplet dissipate everywhere. Eventually, it will go to a zero concentration. So this is what we are these were tracking. But what's the application of this? It's inverse modeling. So if you, example, this is my starting point. I give this image. I want to find out what's the initial image that started. And once you build that neural network, you can also go backwards in time. With diffusion equations, you cannot go backward in time because you lost that information. With these neural networks, you keep that information in the undiffusion equation, so you can get back. So in this case, actually, if I start with this and then I ask you what is the initial microstructure that created this, and go back in the neural network, reverse the trajectory, start from a final condition and go back to the initial conditions. What I'm doing, get back this. So you can use this for inverse problems. You're measuring something, you don't know what happened before. Skip some of this. Here is a general example of a neural network. For the pendulum problem, you would have to position and velocity, output a dissipative Lagrangian, auto-differentiate it. This is not a scientific machine learning. You can always auto-differentiate. And you can optimize. The way optimization is done is by minimizing the Euler-Lagrange equation. Then compare with the x double dot, which comes from the video. So we do like this. You can get back a loss function. You try to minimize the loss. You've started doing some of this for example, I'm showing you the spiral motion of a. You can do this with a neural network. We can even extrapolate the trajectories. The losses are very, very minimal in these cases. It doesn't deviate. So I'll stop here. My next steps would be to extend this to other equations in electromagnetic Schrodinger. You can use it for Schrodinger's equation, viscous flow. If someone is working on fluid dynamics. It's not for real, but then.
Is this kind of physical info?
This is a physics informed, but it doesn't follow the same structure. In physics informed, you only give your inputs are position and time. The output is your variable like temperature. Here, the inputs are you have to give an image input. Physics informed is very simple, and the input is just x, y, z position. Yeah. Here you have to give a whole image as an input, then it outputs the Lagrangian. The Lagrangian is time step to find the next image. So it's a bit more complex.
So how
But it's easier to train.
time divisions between the time divisions is the game. Because I think those formula are based on PDE, right? Yeah, and so you can solve PDE.
Yeah, neural networks need to be trained. Efficiency of the neural networks, once you train, they're very fast. It's just inference. You run it through the network to get an answer. To train it takes time. So you have lots of images. The loss function is highly constrained because it's working at the intrinsic dimension. If you're working above the intrinsic dimension, it's easier to train networks. If you get closer to the intrinsic dimension, it's very hard to train. If you go below the intrinsic, you cannot train the network. So it's like a bottleneck. Advanced networks are hard to train. The Hamiltonian one I showed is faster to train. It doesn't work at the it takes time to train it. Once you train, it's fully reversible. You can go back. You inverse problems. Change your viscosity. You want to figure out what the answer is. You don't have to run a differentially.
Yes, so I have a question. You introduced the intrinsic dimension first and then the Lagrangian neural network. So can I ask, like, is that like you can, if you train with your LLM with the intrinsic dimension, so then that can make this actually work. So that's like the key connection between.
That's the key connection is these Lagrangian networks work at the intrinsic dimension. Because I'm only plotting the phase. The phase space is the intrinsic. You can track the trajectories. The deeper meaning is that any differential equation, if you have a data set that's coming from a differential equation, all the data is basically lying in that initial condition space, the space of initial conditions. Yes. You can always bring it to that dimension and then track the trajectories. So it's easier to understand what's happening.
For the diffusion problem, where you are going back to the initial condition from a solution, right? What if the system is such that it's very sensitive to the initial condition? How does
Those are the hard problems. So noise is a big problem with these neural networks. So Lagrangian neural networks, they are sensitive to noise in the training itself. So if you train with enough noise you do data augmentation when you do the training. If you have noise, it tends to deviate when it gets closer to this point. Initially, it will be good. It's called Lyapunov instability. It happens even in dissipative systems. So if you have, let's say your initial condition was not this, maybe somewhere here. This point is an image. But if you move slightly further here, then it will follow a different trajectory. It won't follow the same trajectory, it will follow the corresponding trajectory for that. But your final answers will all be the same because eventually it's undifferentiable. Problem is when you go backwards. When you go backwards, the inverse problem I was showing, to make a small error in the initial condition here, what should be here can go here. So you're going outwards. This small error is amplified in the inverse trajectory. So it's sensitive to error in the inverse problem. It's not sensitive to error in the forward. Forward diffusion is always correct, even if you have noise. There's small error, but inverse problem is very sensitive. This is well known. The inverse problems always have problems. Weakness of the answers.
so exactly? So what besides that starting image does the neural network know? Like does it know the exact equations?
No equation. It's a diffusion problem. You're trained with diffusion. Knows exactly it's following physics. So if you give an initial condition, it'll do the diffusion problem on that. And if you reverse it, it'll reverse the diffusion, which is not possible. Essentially, reverse it.
I had a follow-up question to the noise issue. Like, for the algorithm of detecting the dimensionality of the data, is there any way to modify or extend that to discover dimensionality for the noise?
Yes, noise has given a lot of problems. Noise is extremely high dimension. It depends on by construction, noise is extremely high. So, for example, Bitcoin has a number, encryption number. You take all the encryption number, try to find the dimensionality of that. It will be extremely high by construction because you don't want people to decode those encryption. That's a 128-bit encryption. So by design, all noise is high dimension. Intrinsic dimensionality of noise will be 200, 300 dimensional. So what we typically do is we use histograms. The histograms, usually if you have enough information in your images is not fully noise. This image has enough information. Noise means that some thoughts here and there. To get the correct dimension, all the noise will go to the tail of the distribution. Don't get that. only 20% of the images will give you wrong answers, 80% still give you. So the ID estimates are usually opposed to noise. But if you have noise in your differential equation, some differential equation called stochastic differential equations, like the ones they use in stock market, they're stochastic, the calculus stochastic. You add a additional term that's noise. None of these methods will work. Lagrangian mechanics will not work. If you have noise, you cannot train them. The initiality is so high.
I see. But then, like for low dimensional noise in those terms, is there any way that's
to the as long as it looks like an image, it's from information.
You how to hate similarity. Because if you try to approach like sure, take this point, how do you stop that?
Oh, the bifurcation points. Yeah, that's some singular points. Again, those points are they are sensitive to noise. Anywhere you have these bifurcation points. Here's the example I showed for a pendulum. I was explaining the pendulum, you oscillate, you give enough velocity, you move the circuit. At that point of bifurcation, where you are giving an initial velocity delta above that point where it goes to the circle, then if you have noise in the system, it won't give you the just physics, because the initial condition is sensitive. What answer you get? It's a critical point where your oscillation shifts from back and forth to a full circle. A small change in velocity at that point you cannot capture. So those are like issues with these. They cannot capture. So different from capturing bifurcation with noise, capturing phase change. Those are all.
Yeah, because the most regularization function, yeah.
Only.
Yes.
They're also discontinuous. Use ReLU and ReLU is a discontinuous function. Well, you can have there are functions, the derivative is discontinuous, but you can have functions where, because you're finding derivatives in all these Lagrangian mechanics, you need to find these derivatives. All the equations I've done with tan h and sigmoid, those are continuous functions. All the derivatives are also. Yeah, ReLU will not work for these things. Yeah.
Ensuring the okay, we were doing this without the organization. Then optimization. Like the adjoint of the equations was that's that we can
That will have relevance. If you can find the adjoint is also differentially. So that you can also track the trajectory, but you'll have to train two networks. One that tracks the forward and one that tracks the reaction. I don't think it's been done, so it's interesting.
this one. When you're thinking of dimensionality in terms of the initial condition, thinking of this from a fluid solid, where the images you're showing correspond to a volume limit. There's flow coming in, going out, like that. So then the flow inside, the images are affected by the boundary conditions.
Right.
How does that?
So that will be intrinsic. The boundary conditions will become intrinsic.
So that will increase the dimension.
So that changes, that acts as a initial condition for your future images. Yeah, that would I would think about this problem. Interesting problem. But anything that changes your trajectories, as long as the trajectories is determined, like money, the initial condition will remain the.
We have a question online. I'm a bit confused about the conclusion on applications for inverse problems. Isn't the fact that the diffusion equation isn't time reversible exactly why you can run it backwards to get the initial conditions back? Of course, it is numerically unstable, so you have to be careful with doing automatic differentiation. So,
yeah, so diffusion equation is not reversible because of dissipation. So any of these equations, when you get closer to a point where all these trajectories merge, you're not inverted. It's not possible. As long as you are on one of the trajectory, the intrinsic dimension of that trajectory is one. Means you can track the location exactly. So this point can be tracked to this point just by following this. Like I said, time of every point being a time snapshot. Follow it. Because these are based on Lagrangian neural networks. As long as there's no noise, there's no bifurcation. They should be able to reverse. You should be able to reverse it. the answer I would give. But these kind of problems I showed you here, it's a simple example just to visualize the latent space. The latent space has two concentrations. And the problem is the two concentrations, two coupled concentrations. So I give an example. You can invert it and go back and forth because the neural network is differentiable in this region. Once you come to a place where multiple trajectories merge, then the noise takes over. You cannot invert it because your derivatives, for example, will fall in the other equation. So if you start from here, you have noise, derivatives of margin noise, you tend to move towards some other trajectory. So as long as the trajectory is far away from this final diffuse structure where all the trajectories will look the same, it should be okay to do the inversion.
Any more questions?
I just want to check on this. Does it matter in terms of the time steps? You go back in terms of like your similar.
Yes, neural networks, you use the time step. You actually have a differential equation here.
Right.
You do time stepping. So time step matters. Yes.
Does this time scale have to be much smaller than the diffusive scale? Or
Right. I haven't done much work on stability conditions for time steps. So you might have something in CFL, even for Lagrangian engineering.
for the context of the inverse model?
In the inverse, I use the same time step. Whatever time step I do forward, I do the inverse. Okay. It is stable. The same time step it will be same. Actually, what time step to use, I don't know. Make sure you can match your own dates.
Does this mean that the dimension of the entire universe is one?
Initial condition, I don't know. Big Bang theory. Initial condition, nobody knows the initial condition.
All these are deterministic.
Yeah, dimension of the universe depends on the initial condition of the Big Bang. Still, nobody knows them. You may come and see.
It depends on your universe. Your universe is exact. What? Very good.
Because everything has come from that singularity, so if you can define variables, it'll be dimensionality.
I was
That's
thinking,
what physicists say, like they have only 18 particles.
I was thinking of it just in terms of time, as you said.
Not time. Time is not long. The initial condition.
Now that we've settled on the dimensionality of the universe, we probably stop. So thank you very much. Oh, there's a question. Next statement.
For the binary data set, why does the L1 norm work? I'm a bit confused. Shouldn't it be according to the dimension of the manifold or number of intrinsic dimensions?
Yeah, so norm is independent from that. Norm is like so norm is the way to find the dimension. The dimensionality is intrinsic to the data itself. It doesn't depend on what distance you choose. But for binary, because the data itself is discretized, the best measure of distance for binary images is the L1 norm. You have to compare the distance to get distances. I think I kind of get this question. Quick answer, sorry. Here, this is. Yeah, so norm itself has no dependence on the solution if the image is not quantized. For example, 1,000 here, you have an image where every point takes a number from 1 to the power 10. 1 to 1,000. So in this case, 0 to 1,000 will give so 1 by 1. Then every norm, this L1 norm, L2 norm, L3 norm, L4 norm, gives you the same answer. But once you use a binary image, because the data itself is 0 to 1, just the nature of the Minkowski norm. If you have zeros and ones, 0 minus 1 square is no different from 0 minus 1 with absolute value. So the L1 norm, L2 norm is the same, but then when you add up all the data, then take a square root, you'll get this factor of half will be different. So just the factor of just a matter of a picture, or you can read the proofs. Simplest answer is you can read these proofs. Give you why it's a lengthy tweet, but you can read. Tell you, for example, for binary images, the intrinsic dimensionality scales with the value of the p norm. So if you use a 2 norm, you get twice the answer. 3 norm, you get 3 times the answer. It's just a measure of the distance that you use depends on the quantization. So it's not really. I use the same idea for them. So it's a different norm.
Very good. Let's thank the speaker again. Thank you.